Hello everyone, my name is Sai Rohit, and now I'm going to talk about the statistical investigation on a dataset called FISH. The FISH dataset can be found in the library called FOS library. Let's just start by calling the library. Before doing that, let's just clear the environment so that anything that's remaining can be gone. So let's call again the library, and then if you do a question mark on the FISH dataset, you can find the description about the dataset. Here you can find that the dataset is about the fishes measurements from the lake near Finland. So in this dataset, you can see like there are different columns, which are first specifying the species, which type of them are, and the weight of the fish. This is the predictor target column for which we have to build the linear model. And these are some of the important predictors for that: the length 1, length 2, length 3, and the height percentage with percentage. So let's just load the data set into our sample data set. And view the data set. Fish data. As you can see over here, this is the total top 6 records of the data set. And we can see there are few NAs for the column 6. Let's just copy this from here and I'll paste it over here. And then let's just describe the structure of the fish data set. So the columns are of the type int, and this weight column is of type numeric, and all are of the different columns. The species is let's convert the species column to factors column. In order to do so, we'll just process data. Let's apply just do by changing it over here itself. And the column number is 2 for the species, right? So we'll apply data and then we'll convert that as factor. So now we have converted the column species from int to factors column. Let's just view the structure of the fish data again. As you can see, we are having the species as the type factor with 7 levels. And then, so for now, dealing with NAs. Let's check how many NAs are there in the data set. So in order to do so, we'll use the isNA command. Let's just check from here. Yeah, just check this fish data. This command will give whether if the column is having a NA result, I mean whether there is a NA value in that column or not. As you can see, all the columns are having false and few of them are having true. So let's just count how many NA values are present in each column. Call some, yeah. See, as you can see, we got one NA result for the weight, and then another NA 87 NA results for the column 6. So as there are a lot of NAs in the 6th column, we are gonna drop that 6th column and then we're gonna process the data. In order to do so, what we'll do is like process fish data equals to fish data minus what is the column number for. Let's check the column number for the six. That's the ninth column. So let's remove the ninth column. Now we got the processed fish data. And then let's see the structure of the processed fish data. So it's having species, weight, length, height percent, width percent. Okay. And as you can see, there are 8 variables. We have dropped the 6 column and we are having 159 observations. And then let me see what else I have to cover over here. Yeah. Moving the column. Yes, we have done that. And just now we'll proceed to the plotting. Scatter plot. Let's plot in order to plot, we are using ggplot library. So I will call that library ggplot. Let's start with ggplot. Data equals to process fish data. And one more thing, we are supposed to remove the NA value. Let's just check the NA values for the process fish data itself also. Is dot NA processed data and call some. So there is one missing value in the weight. So we will deal with that as well. Let's get which value is missing. So which processed fish data dollar weight equals to NA. Let's get the phone number for that. Let's see, is there over here? Let's grab this code, paste it over here. So this piece of code will return the row number for which processed fish data is having NA values. So as you can see, for the row number 14, we are having the NA value. So let's just proceed by removing that from our processed data. Processed fish data minus the center. Yep. Oh, and we will load it to the same data set. Let's just again check whether there are NS present in that or not. Yeah, as you can see, there are no null values in our processed data set. And then we'll proceed with the scatter plot. So we are like plotting the ggplot between the weight and the length of the fish. As you can see over here, the length 3 gives the total length of the fish, whereas the length 1 is from the beginning to the tail, and the length 2 is from the nose to the notch of the tail. So length 3 is a perfect one to take. So I'm taking that. Let's just describe the aesthetics of the data set. We'll plot length 3 x-axis and y equals to weight, and then genome points. This will give us a square scatter plot. Let's just run this code. Yeah, as you can see the data set over here. Let's just add color as well. Color equals to species. Yeah, so we can see that the data set is somewhat like exponentially increasing. So if we check for facet traps, checking weights and length for each species, let's do this. ggplot data equals to this data statistics length, sorry, it's equals to length and y equals to y. That's it over here. Let's zoom points plus facet var species. Let's just check. Let's plot this graph and see the results. Oh, there is no column as length 3. Okay. Yeah. As you can see, this is the plots between the length and the weight, length versus weight for all the 7 species. As you can see that there is an exponential relationship between the weight and the length columns. So this is the length and this is the weight column. There is an exponential relationship between those two columns. So let's try to make this plot linear by applying log to both the columns. Log of length 3 and then log of the weight. Now we can see that the plot has become more linear. So we are performing logarithmic operations so that we're making the data set more suitable for the linear regression. So we can get better results on the data set. Yeah. That's why we are performing the log of the data set. So let's apply that to our data set. Let's just take the column names, call names, C. Again. Length 1, length 2, length 3. So for these columns, we're going to apply the log. So that's why we're going to take them as the column names as input and just force this job. Log process fish data, comma, call names. So by doing this, we're gonna apply logarithm transformation on these 4 columns. Yeah, it's done. Let's just check those values again. Structure. processed fish data. As you can see, the values have changed from over here. See, the weight is around 242, and after applying the log, it's around 5.49, and the same for the length 1, 2, 3 columns. So that's the same plot. Let's just plot again for different species. Data equals to processed fish data in AS. It's equals to length 3, comma y equals to weight geom. And let's do a facet traps on the species. Facet trap species. Yeah. Let's just plot this again. So after applying the log, we can see that there is a linear relationship between the length 3 and the weight. We'll use this data set from now. Also, let's plot the density plot for all the length in each species. Let's plot that by data equals processed fish data, and for the density plot, we are gonna need only the x-axis, length 3, and then geom density, facet wrap on variable species. Yeah, as you can see, the distribution for the each species, the length in each species can be found in this plot. So there are some random distributions for all the column for all the species. As you can see, for the species one, it was like this. Some was like supporting to normal, and it's also random for all the other species. Let's find the skewness of our data set, skewness of the length column in each species. That is done by using the QQ plot. ggplot data processed fish data x equals to, let me check on that. Yep, you're gonna give sample as input instead of x. Sample equals to length 3, and then geom QQ line, and then facet trap again. This QQ plot tells about the skewness of our data set. So in order to verify what type of skewness our data set have, we can find that in our textbook. You can go over here. Let's see the visualizations, a single variable. Yep, it's shown over here. See, if there is a small curve, C-type curve, and then the data is a left skew. If there is this type of the curve, then it's a right skew. And if there is a S-type, then it's a heavy tail one. So if the data is normal, then it will align with the cross line. As you can see in our data set, it's almost normal for some of the columns, and it was somewhat left skewed for some of the species. Yeah, this is one of the visualization from our data. And then let's go ahead with the box plot for the species versus weight. Let's plot that with data equals to processed data is equals to species. Box plot. Height equals to 0 equals to 0.1. Let's see if I'm correct. Yep, 0.2. As you can see, these are the weight is for each species. For the species 1, the weight is around in this range. For the species 2, it's around in this range. And for the species 3, it's in this range, and so on. So this is one of the box plot results. Yep. So now let's begin with the hypothesis test for the mean of the length. For every hypothesis test, there will be like a null hypothesis and then an alternate hypothesis. The result of the hypothesis test is to either reject the null or to accept it. Yep. So let's just begin by finding the confidence interval for the mean length. So in order to find the confidence interval of the mean length, let's just find what's the mean length of our data set. Process fish data and mean of this one. Yep. Let's calculate. It's around 3.36. So let's just begin by calculating the lower limit, lower confidence interval equals. Before that, let's store this as x bar, and then the standard deviation of the length processed fish data dollar. This one as well. As you can see, we are having a standard deviation of 0.4 for the length and mean of 3.36. So we will calculate the lower confidence interval by using this formula. X bar minus, let me look on that formula. Yep, this is the formula. You can use this one. Yep. The formula is nothing but, let me write it over here, like the X bar minus the t distribution, sorry, the sigma standard deviation by square root of the number of observations star the t distribution. This is the lower limit, and then the mean mu, and then again the upper limit will be the same with the plus sign. So let's just write the formula, same formula for the upper confidence interval, which is just changing the minus sign to plus sign. As we can see, we are having, okay, we're having 158 observations. Before proceeding with this, let's just have a look at the length column of the data. Processed fish data, dollar length 3. Yep. Everything looks fine. There are no null values and there is nothing like infinite value. Yeah, so we're gonna use 158 over here, 158, and the degrees of freedom will be n minus 1, so 157, and here as 157 as well. So we can calculate the lower and upper confidence intervals for our mean length. Let's just view those things. Lower CI, it's 3.28, and then the upper confidence interval, yeah, it's 3.44, and we have got the mean value as, yep, it's 3.36. It's inside this interval, and this is the 98% confidence interval for the mean value we have calculated using the normal mathematical formula, and this can be done same using the t.test. So x will be like, let's see what are the inputs for that. Yeah, the column processed quiz data $length 3 comma, and we will define the confidence interval over here. We are doing in 98%, so we'll give 0.9. Let's see what we're gonna get from this, and let's just extract the confidence interval from that. Let's store this to sample result, and then sample result $confidence interval. Yep. Here we got the same values using the t.test, which we have calculated over here. This is using t.test. Let's just perform an hypothesis test for the mean length. Let's assume that the hypothesis for the mean length, null hypothesis as mean length equals to 3.5, and then proceed with our hypothesis test. In order to do so, we're going to calculate that using t.test. The data is processed, this data, and $length 3, comma, mu equals 3.5, then confidence interval level will be 98. Let's see which one we have used over here. It's 99%. Okay, we'll proceed with that one, 99. Yep. So as you can see over here, we have got the 99% confidence interval for the mean, and the mean value, actual mean value. And here is the main thing, the important from the hypothesis test, which is the p-value. Let's just grab that one as well. Dollar. Oh, it's not going to work that way, yes. This result, and then just dollar p-value. Yep. As you can see here, we got a p-value of almost 10 to the power of -5, which is less than 0.05. So this p-value states whether to reject the null hypothesis or to accept the null hypothesis. As the p-value is less than 0.05, we are going to reject a null hypothesis, saying that the mean length is not equals to 3.5. It's never going to be equal to 3.5. That's what the p-value says. So we are going to reject the null hypothesis. Then we proceed with calculating. I think there's nothing left over here. Yep. Hypothesis test for the mean values. Yep. We'll proceed with calculating the type 1 error for that. So now to calculate the type 1 error, we will just replicate it over 10,000 times. Before replicating, let me show you one simple step, what we're gonna do over there. We grab this is over here. Oops, this one. So we are going to do the t-test for a sample that is drawn from the length 3 column, which is of 20 samples, and replaces 2, and the same thing, the confidence level, and we're grabbing the p-value and checking whether it's less than 0.01 or not. Oops, we missed one closing bracket, I guess. Okay, this should not be there. Let's get, as we can see, we got the p-value is not less than 0.01. Let's just replicate this for 10,000 times and calculate the mean for that. Replicate and calculate the mean for this. Yeah, and this mean value gives us the type 1 error percent, which is mean star 100. Oops. As you can see over here, we got a value of 0.079. Let's store that variable to type 1 error and run this again. And now type 1 error star 100. Yep. So we got a 7.51% for the type 1 error, which states that there is a probability of 7% for the type 1 error to occur. And similarly, we will calculate the type 2 error, which is the same. Instead of the less than, we're going to calculate the greater than. Yep, that's it. So replicate 10,000 times. Yeah, now it's fine, I guess. Yep, we got 92.23%, which states that the power for the hypothesis test, which shows that it's 92% of the times it's going to be properly, it's going to give us a proper answer. It can be calculated using power.t.test, and the input values will be, yeah, these are the input values. Let me grab this and explain each of those. So n is over here 158, and delta is the difference between the null hypothesis mean and the actual mean. The actual mean is around 3.36, and we have assumed the null hypothesis mean of 3.5. So that difference we're going to give over here as it is the standard deviation, and the significance level, how much we are calculating for the 99%. Yep. Let's calculate this one. As you can see over here, we got a power of 93%. Yeah. Type it over here. And similarly, we're gonna perform the same hypothesis with using Bootstrap. So before that, we will shift the dataset mean value from 3.36 to the null hypothesis mean value. So for that, we're gonna take wait for boot equals to process freeze data dollar. I'm sorry, we are calculating for the length, right? Okay. Length boot process freeze data dollar length 3 plus mean It's minus mean. It's minus and then plus 3 point. The null hypothesis mean is 5. Yep. Let's run this one. It's done. Let's now verify the mean of our new length boot. It should be 3.5. Yeah, we got 3.5. And in Bootstrap, what we do is like take repeated samples from the original data set, and then we will calculate mean for those samples. Let's just proceed for that. X bar. So we are already having replicate how many times? 10,000 times. And the expression is to sample the length boot and the number of values will be, let's check that. We can take, or we will check all the values. So we'll just replace equals to true. And then we'll calculate the mean for the sample fish. Yep. Sample fish data. Mean of sample fish data. This is, if we run this entire thing, let's plot the hist for the X bar. Yep. And as you can see, let's just add the AB line with V equals mean length. Column equals red. Yep. That's our original mean. And then let's add the original mean value equals to equals to I forgot to add this one. Equals to true. V equals to mean. Color equals to 2. Let's just keep color equals to 1 over. It's fine. Let's just add the actual mean value. Let's calculate this one. 0.36. Okay, it's away from the mean value. Okay, that's what, how I got it. Let's see. Yeah, let's just change the x intervals. X lim equals to c from 3 to, yeah. Now we can see that, right. So this is the actual mean, and sorry, the blue one is our null hypothesis mean, and this is our actual mean. As you can see that, let's calculate the p-value for this. Mean, which will be, yep, this one. How many number of times the mean value will be less than the actual one. Yeah, 2 times this, because this is a double-sided test. Yep. So the p-value is 0, which means we're gonna reject the null hypothesis. Now let's look at the permutation test, which is also similar to Bootstrap. This is also same, comes under the resample type of hypothesis test. So in this, the null hypothesis, the response is independent of grouping. So for our interest, let's just consider the species 3 and 4 from the data set, and we will load them into FISH34 data set. If we view this data set, we can see that the species from 3 and 4 have been loaded into a FISH34. And there is one minus infinity row. Let's just proceed by removing that one from the data set. Let's just first get the row which is having 30 minus, and yeah. See, as you can see, on the 6th record, we are having any minus infinity. Let's just proceed by eliminating that one. Minus. Yeah. Same data set. So if we use the FISH34 data set again, yeah, there's no infinity value source and not any values. Let's plot the box plot for this data set. Plot data equals to fish 34 and x equals to length for y equals to, sorry, we're going to plot only the space x equals to spaces, y equals to weight, and g box plot g ditto height equals to 0, width 0.02. Yeah, let's see this. So for the species 3 and species 4, let's just find the difference between the means for the species 3 and the species 4 weights. Let's just see over here. Plotting that. So we have done for the length column. Let's plot the for the length column over here as well. Yep. So this is for the species and the length column, and we'll perform the same for the length as well. So observe difference in the mean. Let's first calculate the means for the species 3 and species 4. For that, I have already written the code over here. And if you can see, so we'll group by species and then summarize by making M as mean of length 3. Yep. So if we look at M, we'll have two values. This is the mean for the species 3 length, and this is the mean for the species 4 length. So the observed difference is mean of 1 minus mean of 2. And then the observed difference, yep, it's 0.0971. So the difference between the mean for the species 3 and species 4 is 0.09. So let's perform the bootstrap for difference in the mean. As you can see over here, what we're doing is like we are taking the sample from 1 to 30. As there are 30 observations in our FISH 34 dataset, we're going to take a few samples as IDs B and remaining samples as IDs D, and we're going to calculate the mean length for the FISH dataset in the IDs B and for the mean length in the FISH dataset with IDs D. So by doing this, yeah. Now, if we calculate, let's do the p-value calculation. So this is the boot p-value, which is calculated using this formula. And the p-value is 0.15, which is more than 0.15, 0.05. So it means we're accepting that the null hypothesis is true, the response is independent of the grouping. This is for the permutation stage. Let's just plot, let's proceed with the simple linear regression. Before proceeding for the simple linear regression, we'll plot the correlation graph for that. Yeah, correlation. Yeah, you can see that the weight is having a correlation with the length dataset. Okay, yeah, I got what's the problem with the correlation, as we have not removed the infinity value for that. Let's just do the same thing for the process data as well. Yep, this one, let's just grab this and then do for the same. Processed this data, and then let's just send this one as well. Yep, it's done now. Let's just plot the correlation. Yeah, now we can see that the weight is having a linear relationship with all the length columns, which is almost equals to 1. So this shows that the columns length 1, length 2, and length 3 can be used as a powerful predictors for the weight. So we will build the model using length 3 column as the predictor. and the data equals processed fish data. So this is the intercept. This is what we have got the value. This is the slope for the line. So let's store this into our model one, and now we can use that to predict the values, new values. Before that, let's compute the mean error and sum of residuals error. Sum of residuals error can be calculated by mod 1 dollar residuals. Let's do the sum of these things. So we got around 14.8 as our sum of residuals error. Let's calculate the mean error. In order to calculate the mean error, we have to first predict those values. Give that to y bar, predict mod 1 comma new data equals to process with data. Yeah, it's done now. Now let's calculate the mean error by taking the difference between the process $, weight minus y bar. I think we have done something wrong over here. And let me check my original code, linear model. Yes, parts predict linear model. Okay, it's minus 10 to the power of square. Yeah. Let's calculate this one. It's 0.09. So we are getting around 9% error over here. Now let's perform cross-validation. Cross-validation is like splitting the data into training and testing, and then using the testing data to validate our model. So for that, we have already I have already performed leave one out cross-validation, and I'm going to use that function over here, cross-validation. Yeah. The function is this thing. Yeah. The function, let me explain how the function works. The function takes some object as an input, like the index value as input, and splits the data set into testing and training depending on the input object. And then we'll build one model, linear model for that using the train data. And then we're going to predict the values for the test data. Let's just run for this. And now for calculating the error, yeah. So we're going to apply for each of the rows in our data set. So for the first row, if we are performing this, we get a set of error values linear. Yeah. These are all the error values that we got by using the cross validation, and then we'll calculate the mean error. Yes, that's the mean error. Mean errors. We have to do square. So it's 0.98. And in the same way, we got the same error over here, which is also 0.94. So that's it. So what we have done till now is like we have performed visualization on our data set by applying log transformation to make the data set more linear. And we have removed the NA column. I have done some visual plots And then we have done the hypothesis test for calculating the mean value of the length. And then we have done that using bootstrap technique. And then we have performed permutation test as well. And after that, we have built one simple linear regression model based on the length 3 as an input parameter and weight as a target. So let's plot the graph for this, which I have already added over here. It will be, yeah, here it is. Let me just show the graph, how it's gonna show. Add it over here. Yeah. So this is the data set. How the line, the black line is the regression least square line, which it's going to be using for predicting the new values. The length and the way it plots out plotted over here. And in this way, we have built a linear model for the data set, fish data set, for predicting the weight using the length column. Yeah, that's it.